In this video, I'm going to run through the AQA GCSE Physics Paper 1 for the higher tier. I hope you find it useful. Question 1 shows figure 1 where a student is walking across a carpet. And question 1.1 says the student becomes negatively charged because of the friction between his socks and the carpet. Explain why the friction causes the student to become charged, and it's worth 2 marks. So the first mark is saying that friction transfers electrons. The second mark is for stating where the electrons move from. So remember, with any electrical charge, it's always the movement of electrons that's important. You have to have the term electrons to get this mark. So the student becomes negatively charged, it tells us here. So if the students become negatively charged, he's gaining electrons, because electrons are a negative charge, therefore they're moving on to the student. So the second mark is for saying that the electrons move from the carpet onto the student. So as I said, the second mark is saying that the electrons move from the carpet to the student, and that is why the student becomes negatively charged. Question 1.2 says the student's head is represented by a sphere in figure 2. The student is negatively charged. The arrows show parts of the electric field around the student's head. He wants you to draw 3 more arrows on figure 2 to complete the electric field pattern. So the arrows are going to have to point towards a negatively charged particle, because in an electric field, arrows always point towards a negative charge. And they're also going to have to be evenly spaced. So the arrows to be evenly spaced need to be at 90 degrees to one another as shown here. And again, they should all be pointing inwards because it's a negative charge. And that would get you the mark for this question. Question 1.3 says the negatively charged student touches a metal tap and receives an electric shock. And it now wants you to explain why that is. So on screen now I've displayed the answers that the exam board would like you to come up with. So the first mark is saying there is a potential difference between the student and the tap. This causes electrons to transfer from the student to the tap. Here's the second mark. And finally, that earths the charge. So the 3 marks they want you to come up with are all on screen now, so you can use these to aid your answer. In my experience of the marking the papers, the mark most people miss is that there's a potential difference between the student and the tap, which is the first mark. Then, as I said, that causes electrons to move from the student to the tap is the second mark, and the final mark is saying that earths the charge. Question 1.4 says some carpets have thin copper wires running through them, and the student is less likely to receive an electric shock after walking on this type of carpet. It's worth 2 marks, and he wants you to suggest why. So again, here's the mark scheme for this question, just to help us structure this answer. So the first mark is saying that copper has a low resistance, so the carpet has a low resistance. You could also get this mark by saying that the carpet or copper is a conductor. And the fact that this has got a lower resistance means there's a lower buildup of charge, or there's a small potential difference between the student and the tap or earth. And this idea of a lower buildup of charge, or the fact that there's a small potential difference, is what gives you the second mark. So that brings us to the end of the first question. Can you give yourself a mark out of 8? And get ready to move on to question 2. So question 2, so the teacher uses a gauge molecule and counter to measure the number of counts in 60 seconds for a radioactive rock. The counter recorded 819 counts. It does that in 60 seconds. And it also tells you that the 0.3 counts per second is the background radiation. It wants you to calculate the count rate for the rock. So to do this, we need to convert the 819 counts in 60 seconds into a count rate per second. And then we're going to have to subtract the background count from that value. The first thing we need to do is find out how many counts we have per second. So we do that by doing 819 divided by 60. And this gives us 13.65 counts per second. What we need to do now is we need to correct that by removing the background rate. So we're going to have to subtract 0.3 from our 13.65. So you can see I've now put the answers in here. So you get 13.65 minus the 0.3. So then 13.35 is the correct answer. In terms of marks for this question, you get 1 mark for this bit here by doing 819 over 60. 1 mark for getting 13.65. And a final mark for doing the subtraction of 0.3 to get 30.35. That gives you all 3 marks for this question. Question 2.2 says a householder is worried about the radiation emitted by the granite worktop in his kitchen. 1 kilogram of granite has an activity of 1,250 becquerels, and the kitchen worktop has a mass of 180. He wants you to calculate the activity of the kitchen worktop in becquerels. So we know that the granite has an activity of 1,250 becquerels per kilogram, but we haven't got 1 kilogram, we've got 180 kilograms. So in order to work out the activity of the kitchen worktop, we need to do 180 multiplied by 1,250. So you can see that they're working out, activity is 180 times 1,250, and you can put that into your calculator to get the correct answer. And the correct answer is now on screen, being 225,000 becquerels. Again, with this question, you get 2 marks. The marks are as follows: 1 mark for doing 180 times 1,250, and the final mark for getting the correct answer of 225,000 becquerels. In question 2.3, it says the average total radiation dose per year in the UK is 2 millisieverts. Which we'll highlight there. It then gives you table 1, which gives you lots of different bits. It tells you the radiation dosage, so 100 is the lowest dose with evidence of causing cancer, 1,000 is radiation sickness unlikely to cause death, and 10,000 is immediate illness, death within a few weeks. It then tells you the average radiation dose from the granite worktop is 0.003 millisieverts per day. And I should explain why the householder should not be concerned about his yearly radiation dose from the granite workshop. And it also tells you that 1 year is 365 days. So the first thing to do is to work out what is the radiation dose that the person receives in a year. To do this, you use the equation that I've got on screen now, which is the yearly dose equals to 365 multiplied by 0.003. This leads us to an answer of 1.095 millisieverts per year, and that gets you the first mark. And now what we need to do is we need to compare that as a dosage for years, the year compared to this information that we've got up here in a table. And you can see that 1.095 is lower than the average radiation dose in the UK, and it's also significantly lower than these values, which means that the person shouldn't be concerned. So the second mark is written here. It's a lot lower than the 100 millisieverts required to cause cancer, so it's well below the dose with evidence of causing cancer, and words to that effect will get you the second mark for this question. Okay, the final part of the question then is 2.4. It says bananas are a source of background radiation. Some people think that the units of radiation dose should be changed from sieverts to banana equivalent dose. So here's one reason why the banana equivalent dose may help the public be more aware of radiation risks. So this would allow people then to compare the radiation risk to radiation dose from eating bananas. The key thing here is to talk about the radiation risk and how they compare that. Most answers I've marked on this question haven't been specific enough in talking about radiation risk, allowing people to make that judgment by comparing it to the risk of radiation dose from eating bananas. That brings us to the end of the question, so please give yourself a mark out of 8, and then we'll get ready to move on to question 3. In question 3, it says a student investigated how the resistance of a piece of nichrome wire varies with length. It says figure 3 shows part of the circuit that the student used. So here's figure 3. You can see we've got 2 cells to make a battery, the wire here, a switch, and a variable resistor. In question 3.1, it says complete figure 3 by adding an ammeter and a voltmeter. And I want you to use correct circuit symbols. So worth 3 marks. The marks for getting the correct circuit symbols for an ammeter and a voltmeter, and then that will be the first mark. And the second mark is for getting the ammeter in the correct position, and the third mark will be for getting the voltmeter in the correct position. So the circuit symbols for the ammeter and voltmeter are shown here. And the next part is for getting in the correct position. So you must remember that the voltmeter goes in parallel and the ammeter goes in series. So you can see here that the voltmeter is in parallel, and that will get you a mark for the voltmeter to be in the right position because it's across the wire. You get the ammeter in series. I had to put it over a switch here, but it could go anywhere in the circuit as long as it was in series, and that will get you a mark for being in series. And the final mark is for having both the ammeter and voltmeter drawn correctly. That will get you 3 marks to the question. Question 3.2 says describe how a student will obtain the data needed for the investigation Your answer should include a risk assessment for one hazard in the investigation, and it's worth 6 marks. So 6 mark questions are all assessed in the same way. They use these level descriptors here. And you can see that for a level 3 answer, which you get you 5 or 6 marks, the method would lead to the production of a valid outcome, and all steps are identified and logically sequenced. To get the 3 or 4 marks, the method would not necessarily lead to a valid outcome. More steps are identified, but the method is not fully logically sequenced. And level 1, the method would not lead to a valid outcome. Some relevant steps are identified, but no links are made clear. So that would get you a 1 or a 2. And obviously, if you've not got any relevant content, you get a 0. So whatever you write will be assessed in this way. Obviously, these things here don't get you the actual marks, but it's how you write it will be assessed using this format here. So the source of content you should be including is here under the indicative content. And what you want to do there is you want to talk about the following things. So the idea is that you're going to measure length, ideally using a ruler. You're going to vary length using crocodile clips. You'll measure the current using an ammeter. You measure potential difference using a voltmeter. And you carry out repeat readings for those values at the different lengths. You'll then calculate the resistance for each length by doing potential difference over current. You could always plot a graph at the end of that doing resistance against length. That would allow you to see what the pattern is. So the outcome for most experiments doing science is about plotting a graph at the end of it. And potential hazards that you could use would be high current. That may cause the wire to melt or overheat. It may cause burns to skin. So the way to reduce that would be to use low currents. So this is the key piece of information to include. How you'll be assessed is using this grid here. So what I'd like you to do is use the indicative content in order to improve your work and then try and get it into the next level descriptor up. Question 3.3 says, why would switching off the circuit between readings have improved the accuracy of the student's investigation? And the reason why turning it off between readings improves it is because it reduces the heating effect. So when you put a current through a wire, it causes it to heat up. So the temperature of the wire then would not change by turning it on and off between readings, and therefore that would improve the accuracy of your results. In 3.4, it says the student used crocodile clips to mark connections to the wire. They could have used a piece of equipment called a jockey. Figure 4 shows a crocodile clip and a jockey in contact with a wire. So you can see here's the crocodile clip, and you notice it's relatively thick. So there's a larger sort of diameter or length to it when it's in contact with a wire, whereas a jockey is a much finer point. It would say, how would using a jockey have affected the accuracy and resolution of the student's results compared to using crocodile clips? So the two answers we're looking for here is it's going to improve accuracy because it's obviously closer, and the resolution of the length measured will be much higher because we can measure to a higher degree of resolution. And those are the 2 marks for this question. So that brings us to the end of question 3. Please give yourself a mark out of 12. And let's get ready to move on to question 4. In question 4, we've got figure 5 shows a cyclist riding on a straight, level road at constant speed. Question 4.1 asks you to complete the sentences worth 2 marks. It says, as the cyclist rides along the road, the something energy stored in the cyclist's body decreases. So the store of energy that we store in our bodies is the chemical energy. So the answer there is chemical energy. So we've written the correct answer in chemical. We now move on to the second sentence, which says the speed of the cyclist is constant when the work done by the cyclist is something to the work done against resistance. And that would be equal to. So when it's equal to the work done against air resistance, that's when you're going to be going at constant speed. So it's a mark for both of those answers. Moving on to this next part of the question where it's giving you figure 6, and on figure 6 we've got speed in meters per second versus power output in watts. In which to write down the equation that links power, time and work done. So you should know that power is equal to work done over time. So on screen now is the correct equation that power is work done over time. In question 4.3 it says calculate the work done by a cyclist when his output is 200 watts for 1,800 seconds. So we need to rearrange this equation to get work done, and then we're going to substitute these values in. So you can see that we're rearranging the equations we get is work done is power times time. So the answer, so then we do 200 times 1,800 seconds, and that will give us the answer to the question. So here are the substitutions, you can see them on the screen now. So work done is power times time, so work done is 200 watts multiplied by 1800 seconds. If you put that into your calculator, you get an answer, which is the correct answer, of 360,000 joules. So an answer of 360,000 joules will get you all 3 marks. The second mark is for, the first mark was for rearranging the equation and substitute the numbers incorrectly. So this step here will get you 2 marks, and that one there will get you the third mark. Question 4.4 says calculate the percentage increase in the speed of the cyclist when the power output changes from 200 to 300 watts. So what we need to do for this question is we have to get the graph in, so I'm just going to drop that into the question now. I've dropped the graph in the top left hand corner for us to use in this next part of the question. And what we need to do now is we need to look at what speed the cyclist will be travelling at 200 watts, and then also the speed that he'll be travelling at 300 watts. So you can see here at 200 we are one small square below 10, where each small square is 0.5, so that means we're travelling at 9.5 meters per second at 200 watts. And then we're up to 300 watts. You can see that's 2 small squares above 10, which means we're travelling at 11 meters per second. So we need to find the difference now between those two values. So we do 11 minus 9.5, and also find a difference in speed. So you can see here for the first mark we're going to do change in speed is the value we've read off the graph here at 11, and the value we read off the graph at 200 is 9.5. So 11 minus 9.5 is 1.5 meters per second. We now want to find the percentage increase, so we're going to do 1.5 divided by 9.5, which is our original speed, multiplied by 100 to find out the percentage. So here's the calculation we're going to carry out. Percentage increase is going to be 1.5 over 9.5 multiplied by 100. If you put that into your calculator, you get the correct answer of 15.8%. So the marks for this part of the question would be you get 1 mark for getting a 1.5 meters per second, and then you get a second mark for finding 15.8%. The next part of the question, so the maximum speed this cyclist could travel on a level road is 14 meters per second. It then says, how does cycling uphill affect the maximum speed of this cyclist? And he wants you to explain your answer. So on screen is the marks game, and what they're looking for in terms of the answers here is the first one, that maximum speed is lower, because obviously it will decrease if you go uphill. You should know that from common sense and experience in it. But the reason for that is because the maximum power output stays the same, so you've only got the same power output, but you're now, which is the second mark, but you're now having to do work against gravity. So the third mark is saying you have to do work against gravity, or alternatively, you're gaining gravitational potential energy. So your energy being transferred away, you're transferring that kinetic energy away to gain gravitational potential energy, which is why your kinetic is decreasing. And those are the 3 marks for that question. It now brings us to the end of the question 4, so please give yourself a mark out of 11, and please get ready to move on to question 5. Now we're on question 5, and question 5.1 asks you to complete the sentences choosing answers from the box. It's worth 2 marks. The current through an ohmic conductor is directly proportional to something, so that's going to be a potential difference across the components, provided that the something remains constant, and that will be temperature. So the 2 answers that you need there are potential difference and temperature. Alright, so mark for each one of those. So 1 mark for potential difference and 1 mark for temperature. Question 5.2 says figure 7 shows a current potential difference graph for a filament lamp. Explain how the resistance of a filament lamp changes as the potential difference across it increases. So how you're supposed to answer this question is worth 3 marks. You've got the first bit is the potential difference increases as the current increases. That's 1 mark. This causes an increase in temperature is the second mark, because as the current increases, temperature increases because there are more collisions. If there's a higher temperature, that means the ions inside the filament bulb begin to move around more, and that causes an increase in resistance. So those are the 3 marks for this question. Question 5.3 says many householders are replacing their filament lamps with LED lamps which are more energy efficient. What does energy efficient mean? So if something's energy efficient, it converts more of the total energy input into useful energy output. So it converts a greater percentage or proportion of the total energy coming in into useful energy going out. So on screen now is how the examiners would like you to answer it. So a higher proportion of the total power input is usually transferred, or you could have a higher useful power output for the same total power input. So now you've got a light dependent resistor is used to turn on an outside lamp when it gets dark. Part of the circuit is shown in figure 8. You've got figure 8 here. You can see you've got a 12 volt battery, you've got two cells, connected to the light dependent resistor to the outside lamp circuit, and you've got a 2000 ohm resistor there. Question 5.4 says the light intensity decreases. What happens to the potential difference across the LDR and the current to the LDR? So as light intensity decreases, that means that resistance is going to increase. And if the resistance increases, the resistance of this LDR will increase, means it will get a greater share of the potential difference. So the potential difference will increase. But as the resistance increases, the current in the circuit will decrease. So potential difference increases, current decreases. And each one of those correct, we get you a mark. So you get 1 mark for saying that the potential difference increases, and 1 mark for saying the current decreases. In question 5.5, it says, what is the resistance of the LDR when the potential difference across it is 4 volts? And wants you to give a reason for your answer. So if you look over here now, we know we've got 12 volts at the power supply, and we know that 4 volts goes across our LDR, which means we can work out the voltage across our 2000 ohm resistor by doing 12 minus 4 to give us 8. So you can see there we've done the 12 minus 4 to get 8 volts across this one. And now you can see we've got a 2-to-1 ratio, because we've got 8 volts here and 4 volts here, which is essentially that this is getting half the share compared to this one, as 8 is 2 times 4. That means that the resistance of the LDR will be half as much as the resistance of the fixed resistor, so it's going to be half of 2000 to get us 1000 ohms. And the reason for our answer of being 1000 ohms is that the potential difference is shared in proportion to the resistance. So as I said before, we have a 2-to-1 ratio, so we have 2 volts being placed on the 2000 ohms compared to for every volt that is placed on the LDR, and therefore because this value of resistance must be twice as high as this one, so we've done 2000 divided by 2 to get 1000. That's the first mark, and then the second mark is for explaining our reasons. The potential difference is shared in proportion to the resistance, and that gets you 2 marks for that question. The final part of question 5 is 5.6, and it says calculate the current through the LDR when the resistance of the LDR is 5000 ohms. I want you to give your answer to 2 significant figures. So I've now dropped in the figure, so we've got this to refer to through this question. So we've got 12 volts here. It tells us that our value for our LDR is 5000, and that's ohms. And we've also then got that our value for the fixed resistor is 2000 ohms. So what we need to do now is we need to work out the total resistance of the circuit, which we can do by 5000 plus the 2000. And then we're going to have to try and find out where we go from there. So we know that our resistance of the circuit is 5000 plus 2000, which will give us 7000 ohms. So that's now shown on the screen here. So R is 5000 plus 2000, which gives a value of 7000 ohms. We now need to recall the equation linking potential difference, resistance and current, which is V equals I times R, or potential difference is equal to current times resistance. So you can see the equation now, which is V equals I times R, and 12 equals I times 7000 by substituting the values in. So we get 12 volts from the main supply, 7000 is our total voltage. So that would be the first mark for this question. The next thing is we need to rearrange that to find I. So rearranging, we get 12 over 7000 equals I, which gives us our second mark for the question. And then we need to put that into our calculator to find the value for I. Putting that into the calculator, you get an answer of 1.71 times 10 to the negative 3 amps. I get your third mark for the question. And the fourth mark for the question is up here. It's to give your answer to 2 significant figures. So even if you've answered this question correctly or you don't know what to do, if you write a number for 2 significant figures into the current box, you'd probably pick up some marks. So to put it to 2 significant figures, we need to round down. So I is going to equal 1.7 times 10 to the negative 3 amps. So the fourth and the final mark is for giving your answers to two significant figures, as shown here, and by guessing that I is equal to 1.7 times 10 to the minus 3 amps. That's the fourth mark for this question. So that brings us to the end of the question, so please give yourself a mark out of 14. And now get ready to move on to question 6. So this is question 6, and in question 6 it says smoke alarms contain an alpha radiation source and a radiation detector. Figure 9 shows part of the inside of the smoke alarm. So here's the alpha radiation source. It's emitting alpha particles to the alarm circuit, and you can see smoke particles coming in here and disrupting the alpha particles motion. Question 6.1 asks, or states, the smoke alarm stays off while alpha radiation reaches the detector. Why does the alarm switch on when smoke particles enter the plastic casing? So the answer to this question is that the smoke particles absorb the alpha particles, and that stops them reaching the detector. So there you have the answer. The smoke particles absorb the alpha particles, which stop them reaching the detector. Question 6.2 says, why is it safe to use a source of alpha radiation in a house? And the reason for that is that alpha radiation is not very penetrating. It doesn't even penetrate skin, so or it wouldn't even penetrate the plastic casing of the smoke alarm. So you can see the mark for this one is that alpha radiation is not very penetrating. As I said, you could have the idea that alpha radiation doesn't penetrate plastic, it doesn't penetrate skin. Question 6.3 says a smoke alarm will not work with a radiation source that emits beta or gamma radiation, and he wants you to explain why. So the idea of this one is that beta or gamma radiation would penetrate the smoke particles, and therefore there will be no noticeable difference in the count rate when the smoke particles enter the detector, and therefore the alarm would not sound. So the first mark for this question is for saying beta and gamma would penetrate the smoke particles. And the second mark is saying therefore no change in the count rate would be detected, and that is why the alarm would not sound. Question 6.4 gives figure 10, which shows how the count rate detected from the radiation source and the smoke alarm changes with time. You can see here we've got count rate in counts per second, and time in half-lives. The smoke alarm switches on when the count rate falls to 80 counts per second. Explain why the radiation source inside the smoke alarm should have a long half-life. So you can see that 80 counts per second occurs after 1.3 half-lives. So the reason why you've got to have a long half-life is that as soon as you get beyond the half-life to sort of 1.3, then the count rate would drop significantly. So you want to avoid that, and the reason you can do that is by having a long half-life. So how an examiner would like to answer this question is you get 1 mark for saying one of the top points here, which is for saying either that the long half-life means the count rate is approximately constant, or a short half-life means the count rate decreases quickly. And the second mark is going on about this idea of the 1.3 half-lives required for 80 counts per second, and you can see that here. That's the 80 counts per second mark, and you can see it's 1.3 half-lives if you read it from the graph. So until 1.3 half-lives, the count rate is above 80 per second, or until that point it's above the threshold, and after that point the alarm will be activated all the time. So any one of those 3 points there would get you the second mark. And that's how you answer that question out of 2. The final question of question 6 is 6.5. It gives you figure 11, shows a patient who has been injected with a radioactive source for medical diagnosis. You've been given the radiation detector here. I want you to explain the ideal properties of a radioactive source for use in medical diagnosis. It's a 4-mark question, and it's an extended writing one, which means you've got the level descriptors. So how you'll be assessing this question is using these level descriptors. So to get 3 or 4 marks, you need to get a level 2 answer. To do that, you need relevant points, reason, and causes are identified, given in detail, and logically linked to form a clear account. If you get level 1, that's relevant points are identified and there are attempts at logically linking. The resulting count is not fully clear. If you don't attempt at linking content together, you're not really going to get any marks for this question. So now on screen I've got the indicative content, and the sort of things that they would like expect you to be talking about is that you need a short half-life of maybe a few hours so that it wouldn't stay in the body for long. That would mean it would cause less damage to cells, tissues and organs inside the body. It needs to have a low ionizing power, because again this causes less damage to cells and tissues in the body. It needs to be highly penetrating because it needs to escape the body, so you can detect it outside, and so really it needs to be emitting gamma radiation. And so these are sort of the content you need to include in your answer, but this is how you should structure it in order to get into these different levels. And that brings us to the end of the question 6, so please give yourself a mark out of 10. And now we'll move on to question 7. So we now move on to question 7. In question 7 it says, a student investigated how the pressure exerted by a gas vary with the volume of the gas. It tells you here that figure 12 shows the equipment the student used. So you've got a gas tube, a pressure gauge and a pump. A pump will be used to compress the gas in the tube. As the volume of the gas decreases, the pressure of the gas increases. Question 7.1 says the student only recorded one set of results. Give 2 reasons why taking repeat readings could provide more accurate data. And it's worth 2 marks. You get 1 mark for each of the correct responses you give to why it would improve and allow them to collect more accurate data. So for this question, you could have any 2 of the following 3 responses, and that is that you could calculate a mean is the first mark, reduces the effect of random errors. Please note that human error is insufficient, so you can't get a mark for human error, it has to be a random error. Or you could have identify/remove anomalies. There is a final mark for saying that it allows you to test to see if your results are repeatable. And so any 2 of those 4 responses would get you the 2 marks for this question. In question 7.2, it says figure 13, which is up at the top here, shows the position of the student's eye when taking volume measurements. Explain what type of error would be caused if the student's eye was not in line with the level of the liquid in the tube. So here you've got to decide whether it's going to be a random error or a systematic error. So the mark scheme and the examiners were hoping that you go for a random error because the student has misread the reading once. The error is being brought about by a parallax error or a random error, and that will get you the first mark. The second mark is for saying that this happens only once, which is why it's a random error. Again, the term human error is insufficient. You are also credited, however, for saying systematic error if you explain that they viewed it from above or below the line consistently in each measurement. So on the screen now is the mark scheme for the question, so you can mark your work using this. The first mark is for saying random error. The second mark is for saying because the eye position would not be the same each time. As I said at the beginning of the question, you could also get a mark for systematic error if it's clear that the student always viewed the liquid level from above or below the meniscus. If you use the term parallax error, you can still get a mark, but that counts towards the random error mark on this question. Now question 7.3, if the gas is compressed too quickly, the temperature of the gas increases. Explain how the temperature increase would affect the pressure exerted by the gas. You'd answer this question by saying the temperature increase will cause the pressure to increase. It's 1 mark for saying that the pressure increases, as the gas would have more kinetic energy, and the second mark is for saying the gas has more kinetic energy. The reason that is that means that the gas particles will climb more frequently, and that's what causes the pressure to increase. So you increase temperature, the particles have more energy, more kinetic energy in particular, they move around faster, there's more collisions, which causes a higher pressure. So please mark that question. In question 7.4, it tells you that one of the students' results is given below, and it tells you that pressure is 1.6 times 10 to the 5 pascals. It has a volume of 9 centimeters cubed. In order to calculate the volume of the gas when the pressure is 1.8 times 10 to the 5 pascals, the temperature of the gas was constant, so you want you to work out the volume at 1.8 times 10 to the 5 pascals. So for this question, you can use the equation from the equation sheet, which is that pressure times volume is equal to a constant, or PV equals constant. So what we need to do is we need to use the this pressure and this volume multiplied by each other to give us a constant. And we would then know that this pressure multiplied by the volume that we want to work out would also equal the same constant that we calculated here. You can now see here that we've done P times V is a constant, so 1.6 times 10 to the 5, which is our pressure, multiplied by 9, which is our volume, to get 1,440,000 Pascal centimetres cubed. What we're going to do now is we're going to use this constant, and 1.8 times 10 to the 5 multiplied by our volume will also equal this constant. So now we move down here, and you can see that P times V is a constant again. We've got 1.8 times 10 to the 5 multiplied by our new volume, which we're trying to work out, is equal to the constant we've worked out up here, which is 1,440,000. So now we need to rearrange the equation to find V. Here's the rearrangement. We get V is equal to 1,440,000 divided by 1.8 times 10 to the 5. If you put that number into your calculator, you get an answer of 8. When we look at the answer to volume, though, it's 9.0, so we need to write this as 8.0 centimetres cubed. And there's your correct answer of 8.0 centimetres cubed. So for this question, the 3 marks are allocated in the following way. You get 1 mark for this bit to work out the constant. You get 1 mark for substituting that back into there, using the constant and a new value of pressure to work out the volume. And you get a final mark for getting the correct answer of 8.0 centimetres cubed. The final part of question 7.5 says figure 14 shows a person using a bicycle pump to inflate a tyre. The internal energy of the air increases as the tyre is inflated, and he wants you to explain why. So how I explain this is that as you use a pump, you're doing work to the tyre, basically, so work is done to the air particles in the tyre. This means that the air particles in the tyre are going to gain energy, in particular kinetic energy, and that's going to mean that the temperature inside is going to increase. So here we are, work is done on the air in the tyre. It's a first mark. Okay. Now the second mark is saying that either the kinetic energy of the particles in the tyre increases, or the temperature of the temperature increases. So mark for each one of those. And the overall reason why internal energy increases is, remember that internal energy is made up of the potential energies and the kinetic energies of the gas particles inside the tyre, and we're increasing their kinetic energy, which is why their internal energy increases. That brings us to the end of this question, so please give yourself a mark out of 11, and we can look forward to moving on to question 8. Question 8 says nuclear power stations generate electricity through nuclear fission. Electricity can also be generated by burning shale gas. Question 8.1 says shale gas is a natural gas trapped in rocks. Shale gas can be extracted by a process called fracking. There is some evidence that fracking causes minor earthquakes, but shale gas adds carbon dioxide to the atmosphere. I wish to describe the advantages of nuclear power compared with the use of shale gas to generate electricity. So here we're going to be talking about the advantages of nuclear compared to that of shale gas. If we look at the question, we can see that fracking causes earthquakes, which is one thing we can comment on. We can also see that burning shale gas adds carbon dioxide to the atmosphere. If we're adding carbon dioxide to the atmosphere, that's a greenhouse gas, so that will contribute to global warming. And those are our 3 marks that we can pick up for this question. So now I've uploaded these thoughts onto the page, so you can see that nuclear power doesn't release carbon dioxide into the atmosphere. That will get you 1 mark. Nuclear power doesn't contribute to global warming then, because it doesn't release carbon dioxide into the atmosphere, will get you a 2nd mark. This is the main advantage of nuclear power compared to other methods of generating electricity, is it does not contribute to global warming because it doesn't release carbon dioxide. We've also got, that we read from the question, is that nuclear power doesn't cause earthquakes unlike shale gas. And so those are the 3 marks that you should really be aiming for in this question. However, you could have brought in your own knowledge and remember that nuclear power releases the most energy per kilogram of all methods of generating electricity. So you get more energy out of every kilogram of fuel for nuclear power. Question 8.2 says, what's the name of one fuel that can be used in a nuclear power stations? And there you need to talk about uranium and plutonium. The final part of question 8 is 8.3, and it says describe the process of nuclear fission, and it's worth a very generous 4 marks. So here's how you achieve the marks for this question. So there's 4 marks. So remember that nuclear fission is the splitting of a large nuclei to form 2 smaller nuclei. That process releases energy, and 2 to 3 neutrons, which go on to form a chain reaction. But to start the whole process off in a power station, you have to start it off by firing a neutron into the nucleus, and that neutron is absorbed by the large nucleus, and that causes it to become unstable. So the first mark is shown there for saying a neutron is absorbed by a nucleus. So if you had uranium or plutonium in a power station, you'd have to fire a neutron in there first, and that would make that nucleus become unstable, and then the nucleus would split. The nucleus splits into two smaller nuclei. We get your second mark. That process releases energy, or gamma radiation, and it also releases up to two to 3 neutrons, which go on and form a chain reaction. That brings us to the end of question 8, so please give yourself a mark out of 8, and then we get ready to move on to question 9. Question 9 shows figure 15, which shows a coffee maker. The coffee machine uses an electric element to heat water. In question 9.1 it says the coffee machine has a metal case. It asks you, why would it be dangerous for the live wire of the electric cable to touch the metal case? So the reason that is dangerous is that could cause an electric shock. So you can see the answer to that question is that this could cause an electric shock. So any reference to electric shock will get you the mark for that question. Question 9.2 says the power output of a coffee machine is 2.53 kilowatts, which we can just highlight here. 2.53 kilowatts. And then we've also got the machine, the mains potential difference is 230 volts because it's connected to the mains. So they've been quite generous by giving you that information there. I want you to calculate the current in the coffee machine. So we now need to remember an equation that links power, voltage and current. So you should remember the equation that P equals I times V. So there we recall our equation. Power is current times potential difference, so P equals I times V. Now what we need to do is try and work out what we've got. So we try to find current, which is I. We know the mains potential difference is 230 volts, so that can go in straight away. But the power is 2.53 kilowatts, so we need to convert that into watts. So multiplying 2.53 by 1000 will convert our kilowatts into watts, and we get an answer of power is 2530 watts. So we can now substitute into the equation below and then rearrange for current. So you can see down here now, substitute those numbers in. So doing 2530 is equal to I times 230. We rearrange the equation to get 2530 over 230 equals our current. And if you put that into your calculator, you get an answer of 11. So the correct answer to this equation will be 11 amp. So we've got the correct answer of 11 amps here. That'll get you the mark, or all 3 marks if you've got that written down. And in terms of where the other marks are awarded, you have 1 mark for substituting into the equation here, and 1 mark for the rearrangement. If you've used 2.53 rather than 2530, you'd end up getting yourself 2 marks and an answer of 0.011. Question 9.3 goes on to say that the coffee machine heats water from 20 degrees C to 90 degrees C, so we've got that there. We then have the power output of the coffee machine being 2.53 kilowatts. And we also have the information that the heat capacity is 4,200 joules per kilogram degrees Celsius. I want you to calculate the mass of the water that the coffee machine can heat in 14 seconds. And so we've got quite a range of information here. So I think the first thing we need to do is look at the equation sheet, because you can get one of the equations from there. So I've placed the equation sheet, the equation that we can get from the equation sheet onto the screen, so you can see change in thermal energy equals to mass times fluid capacity multiplied by temperature change, or delta E equals mc delta theta. So if you look at that equation, then we have got some of these terms already, so you can see that the temperature change is here, so we need to work out a change in temperature by doing 90 minus 20, and we also have this for heat capacity already. We're trying to find the mass, so that means we need to calculate the energy. But we don't have energy, we've got power. So we now need to use another equation to find energy from power and time. So over here I include the equation that power is equal to energy over time. We know from the last question we have power of 2.53 kilowatts, which is 2,530 watts. We have a time of 14 seconds. So you can substitute that into this equation and then rearrange to find energy. You can now see my working, so I put the 2,530 watts from converting it into kilowatts into the equation here, equals energy over 14. So I need to times by 14 to find energy, so 2,530 multiplied by 14 now. and that gives me an answer of 35,420 joules is equal to my energy. So I can now use this in the equation over here. I can substitute that in for that part, and I'll be able to find out my mass. Before I do that, I'm just going to have to work out the temperature change by doing 90 minus 20. So I've now just done the temperature change calculation by doing 90 minus 20, and that gives me 70 degrees Celsius as my temperature change. I can now go on and substitute all the numbers into this equation now, and then rearrange to find mass. Now that I've substituted those numbers into the equation, you can see here that we've used the equation energy is mass times specific heat capacity multiplied by temperature change. And we've done 35,420 is equal to mass times 4,200 times 70. We've taken the 4,200 times 70 over here to get 35,420 divided by 4,200 multiplied by 70. And if you put that into a calculator, you get an answer of 0.12 kilograms. In terms of marks this question, you get 1 mark for substituting the values into the energy equation, and you get another mark for getting the correct value for energy. You then get a mark for substituting those numbers into the specific heat capacity equation. You get 1 mark for rearranging that, and you get a final mark for working out the correct answer of 0.12 kilograms. That's how you get 5 marks this question. That brings us to the end of question 9. Please give yourself a mark out of 9 and get ready to move on to question 10. We now move on to question 10, which is the final question of the paper. Question 10 shows figure 16, which shows a wind turbine, as seen here. And then 10.1 says, at a particular wind speed, a volume of 2.3 times 10 to the 4 meters cubed of air passes the blades each second. The density of air is 1.2 kilograms per meter cubed, and it wants you to calculate the mass of air passing the blades per second. So we just highlight what we've got in the question. You should see here we've got the volume there, and we've also been given the density. So we're going to need to know the density equation, which you should recall the density is equal to mass divided by volume. We could use that, put our numbers in, and then rearrange to find the mass. So I'll substitute those numbers into the equation now. You see density is mass over volume. I've done 1.2 is equal to m over 2.3 times 10 to the 4. So now I can rearrange this equation to find that m is 1.2 multiplied by 2.3 times 10 to the 4, and that will give me the correct answer to this question. So rearranging, we can see over here we get 1.2 multiplied by 2.3 times 10 to the 4. If you put those numbers into your calculator, you get an answer of 27,600. In terms of whether marks are awarded for this question, you get 1 mark for substituting them into the equation, 1 mark for rearrangement, and then 1 final mark for the correct answer. And that gives you the 3 marks for that question. Question 10.2 says the power output of the turbine is directly proportional to the kinetic energy of the air passing through the blades each second. I want you to describe the effect on the power output when the wind speed is halved. This question is worth 3 marks, and you get the marks talking about the kinetic energy equation. So you get kinetic energy is equal to 0.5 times mass times velocity squared. If the wind speed is halved, then the mass is going to decrease by 2, so it's going to half, which will halve the kinetic energy. But also if the wind speed is halved, then velocity will decrease by half, but your kinetic energy will then decrease by a quarter. So your kinetic energy is decreasing by a quarter due to the wind speed, because it's obviously less, but also because the wind speed is less, that means there's less mass passing the wind turbines, which means it'll also decrease by a further half. So you've got a half multiplied by a quarter, which would get us that the kinetic energy would decrease by 1/8. And that would be the impact on the power. So putting those into words, I'll copy what the mark scheme says here. You see you get 1 mark for talking about what happens to the mass and how that impacts on kinetic energy, 1 mark for talking about how the velocity impacts on the kinetic energy, and a final mark for combining both of those to talk about the actual overall effect on kinetic energy. And that's how you get the 3 marks to that question. The final part of question 10 and the final part of the paper is 10.3. It says at different wind speed, the wind turbine has a power output of 388 kilowatts. The mass of air passing the wind turbine each second is 13,800 kilograms. Calculate the speed of the air passing the blades each second. Assume the process is 100% efficient. So if we just highlight some of the things we've got here, we've got a power of 388 kilowatts. Remember that power is energy over time, so that means we've got 388 joules of energy passing per second, so we can basically just use that like an energy. And we've also got that the mass passing per second is 13,800 kilograms. So we're going to work out the speed of air. So to do that, we're going to have to use the kinetic energy equation, and we'll have to find out what power is in watts. And remember, that's going to be equal to joules per second, which we'll be able to use in the equation. So the conversion for powers up here, so I've done 388 multiplied by 1,000 to get 388,000 watts. And now all I need to do is substitute those into the kinetic energy equation. So you can see here now we've put the equation on. Kinetic energy is 0.5 times mass times velocity squared. And we've put the numbers in, so you've got 388,000 multiplied by 0.5 multiplied by 13,800 multiplied by velocity squared. That will get you the first of the mark for substituting into the equation. We now need to rearrange and find out what velocity is. To get the second mark of the question, you need to do rearrange that equation to get 388,000 divided by 0.5 times 13,800 equals velocity squared, as shown here. And then you can get, from there you can get 56.2 is equal to velocity squared. So either of those things written down will get you a mark. The final mark then is for square rooting that question, that answer, and getting the correct answer for velocity. If you follow this question through, then we get square root of 56.2 to give us a velocity. We get 7.4987 and so on. We can round that number up then to 7.5 being the correct answer for our velocity, and that gets us the final mark. So getting 7.5 here gets us the final mark for the paper and the final mark for the question. So please give yourself a mark after 9 for the question. That brings us to the end of question 10, which is the end of the paper. I hope you found this video useful, and I hope you use this to aid you with your understanding of physics and move forward in the future. Thank you for listening, and goodbye.